and they apply that principle that I just explained to a signal that they generate. They make up all of the probabilities of receiving different things, and if you can see in this graph here, they are graphing the error probability versus the signal noise ratio, and these two top lines here are the probability for a generated signal and a theoretical signal, and these two lines here are after the Viterbi algorithm. So as you can see, the Viterbi algorithm makes the error probability significantly smaller than a signal without it. These signals have a lot of differences. The theoretical signals are very similar. The non-theoretical show, the system, as they call it, shows some, discrepancies. And some of the reasons for that, along with, the algorithm, are that they, in this code, applied a bunch of other noise and a bunch of other filters that we learned in this class to make the signal a lot more realistic. So this is more of what you would see in the real world, because it's not as theoretical of an environment as what I used in my algorithm. So overall, this function is not practical because it's so complicated to compute. And this diagram here, this graph is very simple. The MATLAB code that I used to generate it took about an hour to run, and my computer is relatively quick. So something as simple as an algorithm that goes up to 6.5 dB of noise, signal to noise ratio, and it's just being generated once, to take a whole hour is just not practical in the real world. But it is very effective in decreasing the bit error rate, or the probability of error, as our graphs showed. But it increases decoding time, it increases the cost, because you have to pay the engineer to design all of this, to make it work, and there's a lot of issues, as I discovered, a lot of things you kind of have to think about. And another problem is that it requires knowing a lot of information about the signal that we're receiving. You have to know those probabilities. Like if you show up at the doctor and you feel dizzy, you have to know what's the probability that you have a fever versus probability that you're normal. And when in the real world, when you're receiving a signal, it's not always practical to know probabilities of what you're going to be receiving, because if you knew what you were going to be receiving, you wouldn't need the signal. You wouldn't need any sort of algorithms to decode it in any way, because you would already know. So a lot of times we know nothing about the signal, which makes algorithms like this a lot more complicated and a lot less practical. And also, it simultaneously detects all the users, which adds to the time, instead of just detecting them one at a time. And because of that, the complexity of this algorithm and the time that it takes increase exponentially as the number of users increase. So the more users you have, the more impractical this formula becomes. So what's the right algorithm to use? And one thing that I really learned in this study is that it really depends on what you're using and what your goals are, because MUD, just like any other engineering task, is a lot of trade-off. Do you want complexity? Do you want a perfect signal? It really depends on what you're going for and what you're willing to give and take on. So one of our suboptimal algorithms that we have is called decorrelator, or zero forcing. It has very low complexity for calculations, so it's a fairly common one, but the problem is it enhances noise. As you can tell from this decision formula here, you're inverting your cross matrix, which will cause, if a number is very small, very close to 0, when you invert it, it's going to become infinity. It's going to become very huge. And when you multiply that by noise, you can have your signal be drowned out by this noise because you're really enhancing noise in some cases. But if your cross matrix is large, then your noise isn't bad and it's not a problem. So it really depends on each of those individual components as to whether or not this will work for you. Another algorithm that we have is the mean squared error, or the minimum mean squared error. This one is nice because it does not enhance additive noise. That's achieved by adding this 1/2 of the noise times the identity matrix to your cross matrix before you invert it. So that's really nice. But it does leave some interference when from other users after the transformation. So it's still not perfect at eliminating all of the interference, but it does a pretty good job. Another one we have is decision feedback loop. And how this algorithm works is it detects the strongest signal and then it removes that signal. And it repeats that until it gets all of the signals and decodes all the signals, but it only decodes the strongest signal at any given time. So, it goes through the first time, it says, signal X is the strongest, I'm going to take that out and decode it. Okay, now I'm going to do that whole signal again without X. Now, signal P is the strongest signal, so we're going to take that out. And I'm just giving these letters, obviously they wouldn't be letters, but that's just an example. The nice thing about a decision feedback loop is that you can use it with other algorithms to decrease or to increase the accuracy of your decoding. So you would, pick and choose your favorites and kind of combine them and make it even better. So here's some more MATLAB code that's available on the MathWorks website that just kind of compares and contrasts some of the algorithms. It compares the mean squared error with least squares, which is not one I went over previously, but like I said, there's a ton of different algorithms that we have to offer. And here the mean square is the blue line on top and the least squared is the black triangle line on the bottom. So it shows that mean squared has a better error than least squares. And here it plots the symbol error rate of those two signals. And once again, the blue is on top, so the mean squared error has a higher error. Sorry, so least squares is better in this case, in both these cases. I'm sorry, I misspoke. Anyway, so in the MATLAB Communication Systems Toolbox, they have a lot of algorithms that can really help you see and visualize all these different things. I don't have that toolbox, but I researched them and I discovered that they have all these algorithms that can help you see it. So if you're interested in learning more about different types of mud, here's a list of algorithms that you can use that will help you set the equalizer, and you can display a lot of these things really easy and really well. They even have a Viterbi algorithm, the MLSE equalizer, to show that, so you don't have to write your own algorithm to do that. You just have to get the Communication Systems Toolbox. So there's, like I said, a lot of other adapters, adaptive equalizers, and here's a list of them and how many or number of operations that they have. So obviously, like common is really bad because it's n squared times 2.5 plus 4.5n. So it's very complex, where something like the LMS gradient DFE is good because it's only 2n plus 1. And here's just, some advantages and disadvantages. Like I said, this one's good because it has low computational complexity, as this shows, simple to program, but it's slow convergence and poor tracking, so you're going to have a lot more error with this one. which is, kind of the trade-off. Where with common, its disadvantage is a very high computational complexity, slow as this this number of multiply operations hints at, but it's fast convergence and it's very good at tracking, so it's very accurate. The FTF has 7n plus 14 operations, which isn't too bad. Its advantages are fast convergence, good tracking, low computational complexity, which is something that's very big. You really want to decrease your computational complexity because that increases your cost of building this a lot. But the disadvantages are, the programming itself, the formula is very complicated, so this one still will be expensive even though it's relatively fast, and it's unstable, so it doesn't always work. The gradient lattice has 13n minus 8. It's stable, low computational complexity, flexible structure, so that's very nice. But it's not as good as this one up here, and it has complex programming. Just like when you add DFE to it, still complex programming. The number of operations goes up, it triples almost, and there's low computational complexity still, even though it's a lot more complicated. And this kind of shows, like I was showing before with the DFE, from here to here, you're just adding that and you're making your algorithm better. And here with the common, you can add DFE and make it better. So it's nice to have the option to combine them, as this shows. But moving on, we have our fast common DFE, 20n plus 5, not too shabby. It's fast convergence, good tracking, but complex programming, computation is not too easy and not too low, and it's unstable. Then we've got the square root RLSC, or excuse me, I cannot say letters today, RLSDFE, and it has one of the higher operations because it's got a square term here. The advantages are better numerical properties, it has pretty accurate results, but very high computational complexity. And then our MLSD, as we talked about a lot earlier, it's 2D, so it's exponential. So obviously its advantage is it's the best method, it's going to give you the best results, but it's the highest computational complexity as well, which is bad. And as you can see, that's a major disadvantage for most of them here, and that's not something that you don't want complex really anywhere. You want to keep everything as simple in the programming and as simple in the algorithm as possible, but you still want the best results. So, when you're thinking about which algorithm should I choose, it's a trade-off. Are you willing to pay a little bit more to have this complex programming taken care of for better results? Or is it okay to have results that aren't 100% perfect all the time, to save on your programming? Or is it okay if your users have to wait because your algorithm's slow if they're getting good results? Or are you okay with some inaccuracy if you can make it super fast? Really, these are the things you have to think about when you pick your equalizer. And here's the MATLAB resources that I use. So if you're interested in looking in that, and the comparison of the MMSE versus LS, here's the algorithm for that. And this is the algorithm that shows the MLSE graph, where I was talking about they use all sorts of different filters and noise in there. It's very good, very in-depth. It was really great to study and learn from. So those are two codes that I would recommend looking at if you're interested in learning more. And that's it. Please send me an email if you have any questions regarding my information that I've presented today. And I hope you all enjoyed this class as much as I did. Have a great end of your semester and summer break. Thanks. Bye.